Welcome, everybody. This is Mr. Anderson from Kellogg Community College, Math 130 Statistics. Today we're going to be looking at some story problems that will do z-tests for the mean and hypothesis testing. So from start to finish, we're going to be doing several story problems that will go and test to see whether we should reject or not reject the null hypothesis. Okay, so first off, what we're going to do is take a look at what is exactly our test value. Our test value for z-test in layman's terms is going to be the observed minus the expected divided by the standard error. When we look at a small group that's 30 or more, or if it's less than 30, it's normally distributed, we will use this z-test of our observed average minus our expected average, which is mu, divided by the standard error of the standard deviation divided by the square root of our sample size. And we're going to use the z-test if n is greater than or equal to 30, so our sample size is 30 or more, or if n is normally distributed. Now, what's nice about the book is that they will always give you sample sizes that are bigger than 30, or they will give you, they'll let you know that n is normally distributed. But I haven't found too many examples where the sample size wasn't bigger than 30 to use your z-test. Now, what we're going to do is we're going to go through the 5 steps of hypothesis testing. And when we do all of our examples today, we're going to be doing 5 examples today. Each example will go through 5 steps. So let me move this to more centered there. Alright, so here we go. The 5 steps for hypothesis testing. The first thing you need to do is you need to state, whoops, got this in the wrong clicker there. We need to state the hypotheses. And these are going to be, this is going to take a little bit of time to do because you're going to read it and try to comprehend what is my null hypothesis. And my null hypothesis is the one that you don't really want to change. And then you're going to have your alternative hypothesis, which is either going to be greater than, less than, or not equal to your null hypothesis. The second step is to find the critical value. And the critical value is abbreviated CV, so if you want to write out critical value, that's fine. And you're going to see this on Table E in your book or in the z-test front cover of the book that will have that for you. Table E is also in an appendix in the back of the book as well. Then what you're going to do after you find your critical value, you're going to compare it to the test value that you have to compute. So then you compute the test value, and the test value is going to be x bar minus mu divided by the standard deviation divided by the square root of your sample size. You're going to compare the critical value to the test value, and in step 4 you're going to make your decision, and the decision is going to be either reject or do not reject the null hypothesis. Now this is probably when you're going to want to make a picture of this, and the book will have pictures made in the examples there, but I like doing the pictures because then you see really a visual picture of what decision you should make. Is your test value inside of the critical region on a right-tailed test or a two-tailed test, or if you cover this up, just the left-tailed test? Now you'll notice that we use the words reject and do not reject. We don't use the word accept the null hypothesis, and that's explained on page 418. There's a wonderful paragraph that talks about why we don't say accept the null hypothesis, because we would need to be 100% sure, or we'd need all the data, which is very tough to do in a realistic setting. And then finally, for step number 5, you're just going to summarize the results. And the summary of the results is basically to tell me whether we should reject or not reject the null hypothesis. Making the decision and summarizing it is considered 2 different steps in this book. All right, now you may want to write this down, because I'm going to scroll down the video here and this will disappear, because we're going to take our first problem out of the book. So you have multiple places where you can check the work here, and you'll notice that I changed the wording of the book because I thought, instead of just giving you alpha all the time, I thought about just changing up the vocabulary so you'd have a little bit of chance to try that. So the question is, do cars sit on the lot for more than 29 days? There was a sample of 30 cars that had an average of 30.1 days on a lot with a standard deviation of 3.8 days. With a level of significance of 5%, test the hypothesis. So what you may want to do is you may want to pause the video now. You may want to pause the video now and see if you can come up with your null hypothesis, your alternative hypothesis, and also tell me whether this is a right tail, left tail, or two-tail test. So you've hopefully unpaused your video, and the null hypothesis is going to be that the average number of days a car sits on the lot is 29. See, our question was, do cars sit on a lot for more than 29 days? So this becomes our alternative hypothesis. So our null hypothesis is always something not changing. This is not changing. 29 days is the average, and our question is, we want to see if the alternative to the null hypothesis is correct. Now, this is going to be a right tail test, and it's going to be right tail because we're looking for greater than. Now, the second piece of the puzzle is to figure out, what is our critical value, and we have to take a look at our alpha. Now, in this case, we wanted a level of significance of 5%, and the level of significance means is that we have a 5% chance of making a type 1 error, and that means that this is going to be our alpha. Our alpha is either going to be 10.10, is either going to be 10% or 0.10, 5% or 0.5, or 1% or 0.01. So what we're going to do is, since this is a right tail test, we're going to look on our Z table. So we're going to look on the table for the top 5%. So that's going to be 0.9500, because a right tail test is going to have our the 5% at the top, which gives me a z-score of plus 1.65. Now, you might have thought it was 1.64, but it's evenly balanced between 1.65 and 1.64, so we always round up. So now we're going to compute our value of our x bar minus mu divided by the standard deviation divided by the square root of our sample size. So this is 30.1 minus 29 divided by the standard deviation of 3.8 divided by the square root of our sample size, 30 cars on the lot, which gives us an answer of 1.59. Now here's where we need to compare the z-score to, the z-score, which is our critical value. I should probably put that down as CV. We need to compare our critical value to our test score. So for step 4, let's make a picture of a normal curve, and the middle of it is going to be 0 standard deviations away from the norm. Our critical value, because this is a right-tailed test, was at 1.65. So if our test value is inside of this zone from 1.65 to positive infinity, then we have the ability to reject the null hypothesis. But here is where our test value was. 1.59 was actually less than, not greater than, 1.65. So therefore, since our 1.59 was not in our shaded region, we can conclude using 3 dots, which in mathematics means therefore we cannot reject the null hypothesis. So the null hypothesis cannot be rejected. So the question becomes from the part of the problem, do cars sit on the lot for more than 29 days? Well, according to our data, our small sample did have an average that was bigger than 29 days, but it was not significant enough to change our original assumption, which was cars sit on the lot for 29 days. So we cannot reject the null hypothesis. 29 is the average days that cars sit on the lot, even though our small sample had a bigger average than 29. All right, you may want to copy this down because I'm going to move the worksheet down and do the second problem with you. Okay, so we're going to test the claim that men's athletic shoes are less than $80 with a non-critical region of 90%. Round the shoe average and standard deviation to the nearest dollar. Now, since I have a string of data here, normally what I would do is follow the steps of 1 through 5 to do the things in order. However, since I'm using this presentation system, I have to do all my calculations first, because the calculations could go away once I switch to the calculator or switch to my pen. So what I'm going to do here is I'm going to bring up my graphing calculator, and that way I can show you that I can type in the data. Now I've already typed in the data, kind of saved myself some time here. So you would go to your TI calculator, you would click on the stat button and then hit enter, and then type all the data in list 1. Now I've already done this to save time. But what I need here is I need to get the average and I need to get the standard deviation, and also try to find a way to get all this inside the screen here so we can kind of peruse it here. So I want you to go stat and then write and then enter, and these one variable stats in list 1 will then pop up for you. And we have our average and we have the standard deviation. This is the one that the book will use, and the book is going to round to 19.2. They say that in the directions, but I don't say that in my directions. Mine are a little bit different. And our sample size is 36. So now what I'm going to do is keep this here. I won't be able to go back and access this, but I'm going to go to the screen, draw, and now do the problem with you. I am going to ask you to take a minute and go figure out what your null hypothesis is, figure out what your alternative hypothesis is, and then tell me what kind of tail test this is. Is this a right tail, left tail, or two-tail problem? Pause the video and give it a try. Okay, so the claim is that men's athletic shoes are less than $80. So our null hypothesis, the no change hypothesis, is that no, shoes are 80 bucks. And our null hypothesis or alternative hypothesis is shoes are less than $80. You see that in most of these problems, the claim actually ends up being the alternative hypothesis, and the null hypothesis is saying no, everything's staying the same. Now, since we're going to the left here, this is going to be a left tail problem. So left tail problem here, and we're going to now take to our alpha. Now our alpha is going to be 10% because we chose a non-critical region of 90%, which means that we're going to look for, now since we're doing a left tail test, we're going to look for the bottom 10%. So we're going to look for that on our z-chart. And our z-chart, you may want to pause this and try to find this yourself. The z value is going to be negative 1.28. That's our critical value. Remember, if there's a tie, always round up. So now we've got our critical value of negative 1.28. So we want our test value to be to the left of 1.28 to be in the critical region. And I'll show that to you in a picture. So step 3 is to find our test value. So x bar, whoops, gotta make sure I'm holding the pen right. X bar minus mu divided by standard deviation divided by the square root of n, or the square root of our sample size, which is 75 minus 80 divided by the standard deviation. Now it's in this case I say round the shoe average, which was exactly 75 right there. Okay, And then it says, and then standard deviation to the nearest dollar. Now the book will use this one, which is the 19.2, but I'm going to round to the nearest dollar, so 19 is my answer there. You'll notice below that the other standard deviation that uses a slightly different calculation to find out the standard deviation would also round to 19 if that done that way. So 19 divided by the square root of 36 right there. So 36. Okay, and then we have our answer. If you type that in correctly, you should get an answer of negative 1.58. Now we're going to evaluate whether our test score is inside the critical region. The critical region is determined by the critical value, which is at negative 1.28. Now the shaded zone right there, we want our negative 1.58 to be inside of that critical region to reject the null hypothesis. And it is. That negative 1.58 is inside or to the left of negative 1.28 as it goes to negative infinity. So we can evaluate that 1.58 is indeed less than negative 1.28, and therefore we can reject the null hypothesis. So somebody said that the claim that men's athletic shoes were less than $80, we can reject the idea that $80 is the average for men's shoes, and according to this set of data, the men's athletic shoes, we can reject the null hypothesis and not reject the idea that the mu is less than 80. All right, so let's move on to the next example. You may want to write this down because all of this will disappear once I click on this, and I'll put the graphing calculator away. Okay, here we go. The third example of our hypothesis testing. Get my pen set up right. Okay, here we go. According to the most recent data, the cost of rehabilitation from a stroke is $24,672. From a sample of 35 people at a given hospital, their cost was much more expensive, with a standard deviation of $3,251. Can I conclude with 99% certainty that this hospital is no different than the national average? Perhaps this hospital was under scrutiny because its prices were so high. Well, let's take a second and do our null hypothesis. Okay, and let's do our alternative hypothesis and see if this is a one-tail, two-tail, or sorry, a right tail, left tail, or two-tail problem. So pause the video and give it a try. Okay, unpause the video. We've got the null hypothesis is that no, the hospitals are the average of $24,672. The alternative hypothesis is pretty strict because we're looking that mu is not equal to $24,672. You see, I'm not trying to make a claim that this hospital is greater than or less than $24,672. I'm trying to say that they're different, which makes this the first of our two-tailed tests. So this is a two-tailed test, so it has two tails. Now, let's go with our alpha. Our alpha is going to be, since this is a 99% certainty, our chances of making a type 1 error are 1%. Now, what makes a two-tailed test different, I'm going to put a little star here because two-tailed tests have a little trick to them. We have to look for two different z-values because there's a z-value on the top and a z-value on the bottom. So let's look for the top 1% isn't really 1% because it's 0.5%. If 99%, and I'm drawing just a quick picture right here, if 99% is between these two lines, here and here, if this is 99%, then we want 0.5% here and 0.5% here. So this is what we're looking at. We're looking at these zones right here, which I didn't shade this time, and those zones that are not shaded is going to be on the table at 0.9950 and 0.0050. That adds up to 100%. So our z-score is going to be at plus or minus 9950 and 0.0500. And if you go look at that on the table, you'll see that that is 2.58. So you have two critical values. These are your critical values here. Your critical values are going to be at the bottom part and the top part. So here we go. We're going to run our test now. We're going to run our sample average minus our average divided by the standard deviation divided by the square root of n, which is our sample size. So we had that hospital had an average of 26,300. Whoops, I put a 4 there. 300, yeah, that looks awful. $443 minus $24,672 divided by the standard deviation in this case, which is $3,251 divided by the square root of 35. All right, so you compute that value and you get a standard z-score of 3.04. Woo! Now what I'm going to do is redraw my standard deviation, and instead of shading the non-critical region, now I'm going to shade the critical regions here and here, and this was at 2.58 and negative 2.58. So was 3.04 inside of the critical region? Yes, it is. 3.04 is inside of the critical region on the right-hand side of the tail. So we can see that 3.04 is greater than 2.58, which means that we can reject the null hypothesis. So that hospital is not the national average, and we can see that they are much higher than our, because this is, first of all, this is a two-tailed test. This is a 1% two-tailed test, so we're looking at only 0.5%. And since this hospital is in that top 0.5%, they are definitely not doing the national average. So we got to reject the null hypothesis and tell that hospital to look at the books and figure out why things are so expensive. All right, this might be a good time for you to pause the video and take a quick break because we've got 2 more